Well, a warm welcome indeed. Thank you for being here. Go ahead and get yourselves ready. Grab a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're going to talk about the difference quotient sort of limit definition of the derivative. Now, this is not the ultimate technical definition of the derivative, but if you're in AP Calculus or you're leading up to AP Calculus or just a regular calculus level class, maybe a college calculus class or something, you're going to be presented with something called the derivative. And I have to admit, there's a huge disconnect between how well students understand algebra, average rate of change, slope formula, that kind of thing. In fact, I'll even write. We remember from way back in the day that the slope, which we called m, is simply like the rise over run, right? How far do you go up or down? And how far do you go forward? That's kind of like the run. So sometimes we represented this, once we got a little more advanced, the delta y over the delta x. That is also a way that we thought about this. Okay, so I'm going to help clear up what the heck the derivative is. Not in a super technical sense, but just detailed enough for someone who's taking like an intro-level calculus class in America. I guess they're probably a little more advanced in other countries. But if someone were taking like a Calc 1 class or AP Calculus, like I mentioned, there's a huge disconnect between their understanding of average slope and rise over run, and then this new concept called the derivative, where really there shouldn't be as much confusion. That's where I come in. I come in to really make sure I'm connecting all of the dots along the way. So we're going to work with the natural progression of how we've thought about slope and how that has developed over time. Now that we start talking about functions, there's not just x and y anymore. Sometimes there's t, sometimes there's k, sometimes there's just different variables, right? I'm going to dial things back in time a little bit. We're going to go back to when we just thought about rise over run, the simple stuff, delta y over delta x. Now, first I'm going to point out that we usually consider a function y equals f of x. So the y values that are changing are now really just function values that are changing. When the f of x changes value, the y has changed value, okay? So we have y equals f of x, and we're using this concept to understand rise over run. Let me draw a simple little diagram. We can just have whatever function. It doesn't really matter what it does. I like to use the x squared or some kind of a parabola, but really just something that kind of goes up. And I don't want a linear function, because the beauty of calculus is that we're able to analyze functions which are not necessarily straight lines. We can take curves and we sort of get to use straight lines to approximate what's happening on a curved surface. Okay, so let's find the slope. This is like the average rate of change, right? Some people call it AROC. In fact, that's what the last video was about. It was about the average rate of change. Just a reminder on how we calculate the average slope, or the average rate of change between 2 points. That being said, we need 2 points. There's no rise and there's no delta, there's no change if we only have one spot. We have to consider more than one location so that we can actually observe changes happening. So what I'm going to do is I'm going to call this point randomly, I'll call this x1, because it's the first x value that I want to identify. And then if we look at the function, there's the point on the function. What is that y value? Well, that y value, we could call it y1. But remember that since y is a function of x, y1 is really just the same thing as f of x1. Okay, so you can think of this point in two ways. You can think of the point as x1 comma y1, or you can think of it as x1 comma f of x1. Same thing. Nothing crazy there. Now, this next point, I'm going to go forward a little bit. You can go forward as much as you like. I'm going to go forward out to about right here and call this x2. Again, very reasonable what I'm doing here, right? Nothing mind-blowing. And what is the y value for that one? We're going to call this y2. Again, since and maybe it's not even lined up that well, but you get the idea. What can we call this point now? We can call this point x2 comma y2, or we can simply call it x2 f of x2. All right, so we have 2 points now, and what we're going to do is we're going to try to find the average slope between them. So we're going to take a straight line, which we're very familiar with. We know how to work with straight lines. There we go. Oops, that's not very good through the 2 points. That's not even a straight line. Goodness, that's better. Thanks for bearing with me while I attempt to draw basic lines. I think this one will be even better. Yeah, that one's a little bit better. It goes through both of the points. Now you'll notice that the slope between these 2 points is very different from the tangent slope. So the tangent line sits on the curve and has the exact slope at that point. One way of thinking about this is if we use the example of movement, maybe driving a car. If I'm at a certain location at this time x1, and then I'm at a different location at this time x2, I can use the rise over run method to find an average slope or an average speed on my trip, but that doesn't tell me what the exact speed was at this moment. There is an exact speed at x1, and it's according to the slope of this, which is called a tangent line, which kind of, see how it sort of sits on the curve? It doesn't cut through, it just leans on it. It's almost as if you like took some Velcro and just stuck it right on there, like a straight line, like a little piece of pasta. And you notice that that slope is very different from the average speed. That would mean that at this moment earlier, I have a lower speed, a smaller slope, or a smaller rate than the average slope. But then if we look at the rate at this point, x2, it's pretty steep. In order to sit on the curve, it has to go like straight up like that. And that is clearly a larger slope than the average. So how do we find the exact slope at one of these points? Seems kind of tough to do that because I have an average slope, but the average slope doesn't represent the slope at the beginning of this time period, and it doesn't represent the slope at the end of this time period. What the heck are we going to do? So we have a problem here. It's a tangent line problem. How do we find the exact slope of the curve at a point? Well, what we're going to do is we are still going to use this average rate of change idea. Okay, I'm going to redraw the situation. That is not a straight line. I'm going to redraw the situation. And what we're going to look at now is we're just going to look at those 2 points. I'm going to call this x. And now instead of calling this x1 and calling the next point x2, instead what I'm going to do is I'm going to say, okay, I don't really know how far I want to go forward. X2 was all the way over here, but I want to find the slope at this x value. I want to find what's the slope of this curve, not the one that goes through both points. That's the average. I want to find the exact slope of the tangent. See how I keep redrawing it? It's not just because I don't like the the graph, I'm just trying to emphasize it visually, that we're looking at this. I am also missing it like kind of a lot, but I'm mostly trying to emphasize that this slope that sits on the curve is what's going to represent our exact slope. So how do I get this average slope? I'll draw the average slope again. How do I get this average slope to become the exact slope? Well, what I have to do is I have to move this point closer. See that? I have to move this point a little bit closer. Oopsie. If I move this point closer, what starts to happen? Take a look at the quote-unquote average slope. See how that's becoming much closer to the tangent slope? I'll show you. I'm gonna move the point away again. Let's move the line out of the way. If I move the point over here and put the tangent line back, see how this average slope is like? That's pretty far off from the actual slope there. But as I move the point closer, and let's see if it's going to move that line. As I move the point closer, these average slopes start getting closer to the exact slope. So I don't want to call this x2 because that's going to hold it in place. It's going to fix it there. I don't want to fix it there. I want to move the point anywhere I want. So what I'm going to do instead is I'm going to say, okay, from x, we have this little gap, which we're going to call h. Therefore, the second point, wherever the second point is at, is going to be called x plus h. Okay? So now we have some slightly different expressions. This is our y value, which we're going to call f of x, because it's the y value determined by the function. And then I'm going to call this y value f of x plus h. And I get to play with the h. I get to adjust the h. I can adjust the gap. How far do I want these to be spaced out? Let's write the average slope. Remember, it's the y, the change in y over the change in x, or in this case, it's the change in the function value. So it's like y2 minus y1 over x2 minus x1. But instead of y2 and y1, and instead of x2 and x1, I'm going to call this f of x plus h minus f of x over, instead of x2, I'm going to call this x plus h minus x. And this actually simplifies. Right? Basic arithmetic. You have a minus x, so we can cancel the x and minus x. And we end up with this very interesting expression, f of x plus h minus f of x over h. And you may have seen this. It's called the difference quotient. Yeah, it's called the difference quotient. And what the difference quotient represents in this case, this represents the average rate of change, or the average slope between 2 points, which still is not a tangent line because a tangent line only sits on 1 point. So how are we going to turn this average rate of change, or this average slope between 2 points, into a single point? Well, we're going to use the new concept that you saw in pre-calculus called a limit. We're going to take a limit as h goes to 0. What does this mean? Limit as h goes to 0. What does h represent? Think about it. What does h represent? H represents the gap between these 2 points. Well, I want the gap to essentially go to 0. I want these points squished up right on top of each other, basically, like if they had to squeeze into a single chair. You ever played musical chairs, and at the very end there's just one chair, or even if there's only a few of them left and people are just trying to squeeze themselves both into a single chair? That's what these 2 points are going to do. Now, by doing this, I have an approximation for what we call the derivative, and we write this little apostrophe on it. We say prime. You might remember that from geometry. Sometimes we say prime. This is called f prime, which represents the exact slope. So this takes the average between 2 points and turns it into an exact slope at 1 point. That is the beauty of this. And like I said, this is not at all the formal technical definition for a derivative. There's a much gnarlier definition with some Greek letters involved. We're not going to traumatize you with that. But if you're interested, look up the epsilon delta limit definition of a derivative, and that will get you closer to understanding, but also confusion. That's kind of how math works sometimes. This is what you're going to be using in a standard AP Calculus class. You're going to be using this definition of the derivative for a little while, just so that it's very clear how to find the exact slope at a point. We need to squish 2 points together so close that they basically are sitting on top of each other. Remember that this doesn't mean h equals 0. We're not saying that the gap is 0 so that they're literally the same point, but we're sending the gap to 0, so we're squishing them closer and closer together, like a couple of magnets, right? They're never going to be exactly touching if they like repel each other, but they're going to get so close. Now, how is this useful in practice? What does this even look like for a function? Well, this allows us to find the slope of a tangent line on any function, but we're going to start off and kind of finish off with some sort of basic examples. So we're going to take the function f of x equals, I kind of spoiled it earlier, I'm going to use x squared because it's kind of the most basic type of equation or function that has some curviness to it, but isn't too complicated. It's almost like as simple as you can make it without being a linear function. So if we have a function f of x equals x squared, and we want to find the slope of the line tangent to f of x when x equals 4. And they have to specify this if they want an exact value, because you'll notice that the graph, maybe I'll just draw x squared again as best as I can without wasting too much of your time and butchering the graph. What did I just say? Something like that. I think you'll accept my parabola, right? I shift a little bit. You guys be a little happy if I shift it? I gotta admit, that looks much better. So what I want to notice is that I need this point x equals 4 because the tangent line, I can draw a bunch of tangent lines. The tangent line changes depending on where it's touching the graph. Like, what spot do I want it to touch? It's going to have a completely different slope. Here at the bottom, it has like a flat slope for a while. You see all those tangents? It's like this one touches here, this one touches here, kind of. Not really, so maybe I should move it. There we go. This one touches here. You can see these points of tangency, and you'll notice that depending on where we're at on the curve, it has a different slope. In fact, that's why it's not linear, because as we move along the curve, the slope is changing. You can kind of imagine being on this roller coaster, and if you're on the roller coaster and looking straight, your line of sight, like the things that you're looking at, are going to change just naturally because the curve of the actual track of the function. So like when you're going straight down, you know what that's like if you've ever ridden a roller coaster, and then you're about to like come up, you're going down in a dip and about to come up. So your line of sight is sort of increasing. It's getting taller and taller and taller. And so we should expect that when x equals 4, this thing is pretty steep, right? Because we know that x squared gets steep pretty quickly. I am missing. It's like Shaq shooting free throws here. We can see that as x equals 4, we have quite a steep slope. Okay, so let's use this sort of limit explanation of the derivative to find this. Oh, and I should mention again, f prime represents the exact slope at a point. All you have to do is plug in an x value, and that will give you the slope. So let's represent the slope of this x squared. it's going to be approximately the limit as h goes to 0. You should get used to writing this structure down every single time. Limit as h goes to 0, f of x plus h minus f of x all over h. And so what we need to do is we need to take our specific function x squared into account. Now I put f of x because that's the general difference quotient, but in this case we're asked to find the slope of the line tangent to this function in particular. So f of x equals x squared. Here's another thing where students get tripped up on. They know where to put f of x. They know how to replace that. They just say, oh yeah, that just goes there. It is a huge pitfall, and it's sad to see because I know they're not far off. I know they understand what they're supposed to do. They just don't realize they understand what they're supposed to do. When students say, what do I do with f of x plus h? What does that look like? Just think about it very simply. What is f of 3 for this function? People would just say, oh, 3 squared. You just plug in the 3. Duh. And so what is f of a? Oh, it's just a squared. You just plug in the a, right? Duh. What is f of x? Well, we already know that one. It's x squared. Duh. So then what's f of x plus h? Crickets. That's what I hear. I hear crickets. Just plug in the x plus h. They think that because it has a plus that you're not like allowed to plug it in there. You could totally do that. If I asked you what's f of 3y minus 7z plus 12, I mean, I wouldn't ask you that. That would be kind of weird. But you would just plug whatever's there into where the x is. You're just replacing it and squaring it, right? So that should clear up the confusion of what we're going to do with f of x plus h. That means that the derivative of x squared is the limit as h goes to 0 of x plus h squared minus x squared, right? I'm just replacing f of x plus h, and I'm just replacing f of x, and this is all over h. Now, of course, I want to try to plug in this limit value of 0, but if I plug in a 0, I'm just going to get 0 over 0. That is no bueno. We can't have anything divided by 0, let alone 0 divided by 0. That's even weirder. So what we have to do is simplify this inside first. Hopefully, we can cancel this h out. I mean, I can't just like say bye-bye. It's gone. But hopefully we can cancel it out somehow. Let's trust the math. I see that there's a squared in here. Let's work that out. So this is x plus h times x plus h. And then that's minus x squared all over h. Do we have to write limit every single time? Yeah. Be annoyed. It's fine. You'll get the answers right, and that's what matters. This is going to turn into x squared. You should be very comfortable with this at this point. Plus 2xh plus h squared. If you need to review FOIL, feel free to go back to Algebra 2 and then come back when you're ready. Now, at this stage, very important, once we've kind of worked out the top, this will always happen. Everything with an h, without an h, must cancel. If it doesn't, then you did something wrong. Literally. Okay? So this is going to be equal to limit as h goes to 0 of, what cancels? Anything with no h. See that? So we have 2xh plus h squared over h. This is promising because now that there's only h stuff left in the numerator, I can factor it out. And when I factor things out, I can cancel. Now here's another point of contention. Students tell me this all the time, and I'm glad they're thinking critically about this. I love this question, honestly, because it tells me that they're paying attention. They say, hey, wait a minute. You can't cancel h on top and bottom. And I'm like, what? Why not? It's h. Same thing on top and bottom. I said, hold on, but h is 0. I'm about to plug in h equals 0, and you can't divide 0 over 0. And I say, oh, very observant young one. You are correct that we cannot divide by 0. However, this limit as h goes to 0, that does not say h equals 0. I know it looks like it does. I know we're even going to replace h with 0. So you have many reasons to think or suspect that h is equal to 0 here, and therefore that would mean we can't cancel it. However, the fact that we're saying limit h arrow 0, let's go back to our description earlier. We're not saying that they are literally on top of each other. They are not the same exact point. They're just really, really close. They're almost touching. So h is like almost 0. Almost. And therefore, we can cancel it. Because limit as h goes to 0, it actually quite literally means that h is not 0. Or we wouldn't have to write the word limit. We wouldn't have to write the word limit because limit means that we're getting close to this situation. As close as humanly possible. We cannot get so close that h equals 0, or we would have some kind of like destroy the universe, divide by 0 kind of thing. We'd all be living in like a Fallout right now. So since we can cancel the h's, now we have limit as h goes to 0, 2x plus h. And now you can plug in h equals 0 with no issues. And we get 2x. What the heck does that even mean? So f prime, which represents what? It represents the slope of the tangent line, which we call the derivative. The slope of the function at a certain point is equal to 2x. So that means that if we have the x value, we can find the slope of the tangent line. Tangent line at that x value by using this new expression called the derivative. And actually this is a function. So we say f prime of x is the derivative of f of x, but it is also its own function. And so if we want to know the slope at a certain point, like 4, now you can simply plug in x equals 4, and that gives you the slope of this curve. So as mentioned before, if we look at the x squared curve, the slopes are constantly changing. In fact, whenever x is negative, notice on the left side, all of those slopes are also negative. It's going down. But as x is positive on the right side here, all of those slopes go up. And this is consistent with the fact that the equation for the slope is 2x. What happens if x is negative? The entire result is negative. And what happens if x is positive? The entire result is positive. So this was a brief, informal way of getting you introduced to something called the derivative. Big picture ideas here are that the derivative tells us the exact slope at a single point, and it comes from using the old school definition, average rate of change, rise over run, whatever you want to call it, y2 minus y1 over x2 minus x1, however you want to phrase it. That average slope between 2 points becomes the exact slope as we push the 2 points irresponsibly close to each other. Okay, so the tangent line problem is solved. How do we find the exact slope of the curve? We take a limit of the average slope as the 2 points approach each other. Now, which point do we want to approach which? I could have also done this argument by starting with this x value and saying x minus h, but I didn't feel like doing that. I just wanted to go backwards. The overall point is that when the gap between them closes, that gets us to the tangent line. Okay? So I really hope you learned something today. I encourage you to try another problem. Actually, I'm going to leave you with the problem. I don't normally do this, but I'm going to have you try. Find me, I'll type it, it's faster. Okay, the slope of the, let's make this a little longer. Slope of the line tangent to the graph of f of x equals at the point where x equals negative 2. And the function here is going to be x cubed. Yeah, I want you to find the slope of the line tangent to that curve, f of x equals x cubed, when x equals negative 2. Give that a shot. Feel free to leave your responses and any questions in the comments. That's enough blab out of me. I'll see you guys next time.